let's quickly wrap up our linear algebra review. There are two more things I need to tell you. The first is about projection matrices. In particular, orthogonal projection matrices. So we call a matrix projection matrix. Let's say it's a square matrix in Rm by M if projection matrix if it is symmetric. If it is symmetric, and if I apply it twice, then I get the same matrix back. This matches our intuition of a projection, because once you project a point somewhere, then it should stay there even if you try to project it again. Right? So the important part for us is just that if I have a projection matrix, then I know that the eigenvalues, and note that I'm assuming that it is symmetric. So in particular, the spectral theorem that I just showed you holds. So all eigenvalues lambda I of H are either +1 or 0. How do we see something like this? It works like that. You pick an eigenvector, vi of H, and then you write down what it means to be an eigenvector. So you start with, you take the vector vi, you take a transpose and hit H times vi with that. And we know that vi is an eigenvector, so this is the same as lambda I vi transpose. So this is lambda I times norm squared vi of vi. And we assume that this is non-zero because it's an eigenvector. We don't allow 0 as an eigenvector. So, but in other words, we know that applying H once is the same as applying H twice. And we know it's symmetric, so it's the same as writing H transpose HVI. Now we're using facts about the transpose, namely that I can write this as HVI transpose HVI. And now we use again that that vi was an eigenvector for H. So this is lambda I vi transpose times lambda I vi. So lambda I is a scalar, so I can put in front lambda I squared times norm squared of vi. And if we compare these two sides, we just said that vi norm squared is not going to be equal to 0, so we can divide by that. In other words, lambda I is equal to lambda I squared. And lambda I is a real number, so the only real number that fulfills this, the only two real numbers that solve this equation are 0 and 1. Great. So we'll have to use this to actually simplify some of the matrices in our pivot in a minute. So the second thing is, let me just quickly review the trace with you. So the trace of a matrix in Rm by M is defined as the sum over the diagonal elements that I'm just going to write as AII. And there is an important fact about the trace. If you have three matrices that work out so that the product A times B times C is a square matrix. So OK, let's see. Let's say A is N by M, B is M by L, and C is L by, and now I need to be careful, this needs to match the N here, L by n, then I can multiply all of them together. I can calculate the trace. Then trace of A times B times C is the same as cycling through cyclically. So that means I can put the C, I can take the C from the end and put it in the front. CAB is the same as trace of, I can do it again, I can put the B in front. BCA, and we see that all these things will still end up being square matrices. For example, here, B is m times L, C is L times n, A is n times m, so we end up with an m by m matrix. And they are all equal. Mind you, this is not true for the other permutations of these matrices in general. OK, so in particular, what this implies is if I have, let's say, a spectral theorem for A, and I write A equals V lambda V transpose, then what happens here is that the trace of A is trace of V lambda V transpose. And I can play the same trick. I can put the V transpose in front. And because we assumed V to be orthogonal, this is just the identity. So we have trace lambda, which is the sum over all eigenvalues. In other words, whenever I have a matrix and I take the trace of it, what I get back is the sum of the eigenvalues, at least if it's, let's say, it's a symmetric matrix for all we know right now. And this is also going to be useful to calculate some eigenvalues later. OK, so now let's get back to doing statistics. Actually, while I'm erasing, you maybe should try to verify some of these properties here, also the ones from the previous video, to see if I'm actually telling you the truth. You can just go through some examples and see that each of these things actually work out. And when we're back, we're going to finally try to find the pivot here.